Okay, good afternoon, everyone. Hopefully you can hear me. Actually, can one of you confirm? You can hear me, right? Nope.
Yeah, we can hear you.
You can. Okay, great. Okay, thanks. So, um, just a reminder, today is the late deadline for design assignment 1. So, making use of 3 late days. So, don't forget. Let's see. Then I guess I had posted some things on Piazza, so you can take a look at it. So today's plan, one key thing about this week is that the Wednesday lecture, unfortunately, I'm having to move. So my plan is to record it 6 to 8 p.m. tomorrow. So if any of you want to join just to listen to it live, you're absolutely welcome to. Otherwise, I'll post the recordings. It would be on the next module, which is on timing. Okay, so today's plan is that I'm going to wrap up the discussion around sequential systems, and then we are going to move to making more complicated sequential systems, one which have kind of a state graph type structure where you kind of jump from state to state and all, but also sequential systems that process data. Okay, so we're going to look at that. So at the end of last lecture, I was kind of talking about that how for some cases, these were just sort of motley topics. And one of the things I had mentioned was that how for some cases, there's kind of a simpler, inefficient, but workable approach, which is called a state vector approach. And kind of the idea is that in many sequential system problems, essentially my answer depends upon looking at some recent history of Windows, okay, some presumably small enough samples, so like the latest current input sample, the one previous to that, the one previous to that, maybe some window of size k, and everything I need to do kind of can be done on that. So like, for example, like one of the examples that we had studied earlier on in the lecture, I want to look out for a pattern UCLA, successive letters in the input, for example. In that case, we know that all I care about is the current and the previous 3. On the other hand, there are problems where that window may be much, much larger, in which case a more efficient technique would be needed. Like, for example, the problem I had about whether it's divisible by 7 or not, right? The number seen thus far since we started. So if you were to simply store the history, you will need infinite history. But for the first class of problems where I'm looking for a pattern over a small number of recent samples, an approach that works well is that we basically store all those previous samples. And that's kind of the idea behind the figure that you're seeing out here, which is inputs are coming here. So let's call the input X, right? Inputs are arriving. And so what is happening is that if I were to examine this input, is the one which is entering the system. The sample out here, the input on the between the first 2 flip-flops, that's kind of an older sample, the one from the previous clock tick. And then likewise, the one in between the second and third flip-flop, the second and third register is the one which came 2 clock edges ago. And then finally, the one which is out here came even further back, right? So every time, if you think of a D flip-flop, what it does is at a clock tick, it copies what is on the input and puts it on the output. So effectively, it adds a clock tick delay. So anytime I'm now looking for a pattern, and in this particular example, the pattern that I'm looking for is that I have 2-bit values coming in. So these values are 2-bit. And I'm basically looking for this pattern that there is a sample which is larger than the previous sample and the next sample. So if xt minus 1 is the sample that I'm looking at, then we are saying the sample which came before it, xt minus 2, is smaller, and likewise the sample which came after it is also smaller. It's kind of defining a peak in a crude manner. And so what I can do is I can kind of have, depending upon how you define it, but let's say I could say that I'm looking at these 3 samples. Okay, the one after the first flip-flop, after the second, after the third, and then I can use some comparators and then an AND gate to kind of do this equation that we have out here and have an out on it. So in this case, I don't have to draw any complicated state diagram and all. I'm basically, my output specification is literally in terms of the input. I'm kind of defining what y of t looks like in terms of input samples directly. And a lot of problems, particularly pattern matching problems, are like that. Now, the disadvantage out here is that I'm using 6 flip-flops, right? I mean, each stage is a register, and I need 2 bits, so it's total of 6. The reason we don't pick, like you might wonder, why did I not work with this, and this, right? I mean, like, so if I were to mark it, right? I mean, let's just call it 1, 2, 3, and 4. I'm using 2, 3, and 4. I'm not using 1, 2, and 3. And the reason is because X is coming from the outside world, and that therefore it is not necessarily stable, right? Because the outside world, unless it makes an explicit promise that X will change only on clock ticks, I cannot make use of X. So for designs like these, it's safer to work with output X after it has kind of been clocked into the system. So that's the reason the way it is structured. So I have now 6 flip-flops, 64 states. But if you kind of think about this problem, that what are the different cases that can occur? So you can think in terms of, like, I may have a pattern where xt minus 2, xt minus 1, and xt, they are rising. Or xt minus 2 is rises to xt minus 1, so, but then it is stable, right? So you can think in terms of different relationships that can exist between these 3 samples. And it turns out that there are a total of 8 such relationships, okay? One way of thinking, so there are a total of 8 such relationships. And so if you were to actually solve this problem using the finite state machine approach, where you draw a state graph, think in terms of what states do I need to remember, it turns out that you can do this problem with 8 states. In other words, you can do this problem with 3 flip-flops, as opposed to doing this problem with 6 flip-flops, okay? But obviously, this one also requires some thinking. But the advantage grows rapidly. Let's say, what if I had defined a pattern over the recent 100 samples? Then then this approach, the state vector approach, can become much more inefficient. But just want to throw that out, that this is a quick and dirty way of working with. Anytime you have a problem where output can be specified as a function of input, current input, and preceding input, right? If I can describe in those terms, then this approach actually works pretty nicely. Those of you who have done ECE 113, signal processing, digital signal processing, this should probably remind you also of, like, the way we think about FIR filters and IIR filters. They are basically special cases of these kind of machines. In case you haven't done it, you'll kind of see it later. Okay, so just wanted to mention that the state vector approach is a simplistic way of doing things, but is inefficient for generally inefficient. The other thing I just wanted to spend time before we close this module is this whole issue of Mealy and Moore. And I had made a comment early on that the two are functionally equivalent, in the sense that you give me any problem, I can express it at Moore and I can express it as Mealy, ignoring timing a little bit, okay, in the sense that purely from a software point of view, if you may, where time doesn't, if I'm looking only at the functionality and not the timing, then I can always translate Moore into Mealy and back. And that's what I'm going to spend some time on. Again, just to remind you, Moore machine is one where the output only depends on the state, and typically we write it as part of the state itself. So this is saying state S1 with output 0. It's 1 bit output, 1 bit input in this case. Whereas for Mealy machines, since output depends upon the input also and not just the state, the output always go on the edges. So 1/0 here means that I'm taking this edge if input is 1, and by the way, I'm going to put 0 on the output. I could also write Moore machine also in the same way. The only thing that you will see is, like, instead of writing it this way, I could write it as 1/1, 0/1. I could write it like that too. You'll just to check that state machine is more, in that case, you'll have to just make sure all outgoing edges of a state have the same output. Mealy react faster, right? Because as soon as the input changes, the output can reflect that. Whereas more, because it depends only on the state, so the effect of any change in input will be manifested at the next clock tick. Generally speaking, more needs more states, whereas Mealy can get away with more needs more states, and Mealy can get away with fewer states. On the other hand, more generally tends to have simpler combinational circuit, whereas Mealy tends to have more complicated combinational circuit. Part of it simply is because the output depends upon both input and state. Very importantly, not only does the state change at clock tick, but in case of more, since the output depends on the state and state is changing on clock tick, so output is also kind of changing only at the clock ticks, right? A little bit of a delay, but basically clock tick. Whereas in Mealy, since output can be changed by the input immediately, so output changes are not aligned with the clock tick. Okay, so that's what we mean by asynchronous, is asynchronous to the clock. We'll see shortly that more has a big advantage, that it's kind of visually more compact. It's kind of like we are aligning output to state. So we are kind of basically saying that the states reflect some output functionality. Whereas in case of Mealy, it's a transitions which associate with the output. More tends to be easier to design, easier to conceptualize, or at least I guess I find it by most people, but I see many students kind of naturally end up thinking Mealy. Generally, I would say I frown on Mealy for hardware design. Mealy is perfectly okay if you are doing a software finite state machine. Finite state machine exists in software systems also. Mealy is perfectly okay there. It has advantages, but more on hardware side carries significant pluses on balance. So let's talk about how can we switch back and forth between them. So converting more to Mealy. So first, let's imagine I'm given this machine, right? This more, I've given both the state diagram. You can verify, you can verify that the table and the graph correspond to each other. X in state X output is 0, in state Y the output is 1, and in state Z output is 2. And then, of course, we have the transitions. The input can take 2 values, 0 and 1, and output can take 3 values, 0, 1, and 2. So again, next state, we have sort of separated out the case for input equal to 0 and input equal to 1. So if I'm in state X, if input is 0, I stay in state X. If input is 1, we go to state Y, and so on and so forth. So how do we make a Mealy machine out of it? So kind of the idea is that we start with the state machine, the state table. And then what we do is we are, instead of output being associated with the state, our goal is that output is going to be associated with the input now. So what we do is we pull this output column into the next, make a new column, next state, comma, out. And then for the two cases, in 0, in 1. So here we had an X, now we have X and whatever was out, X, comma, 0. Okay. Sorry, let me explain. So what we do is we look at this next state, and then we see what is the output associated with that state. So here the next state is X, and for X the output is 0. So we write X, comma, 0. Under n equal to 1, next state is Y. We look at Y, and we see Y would have output of 1, so we put Y, comma, 1. Likewise, Z, the output with Z is 2, so we put Z, comma, 2. Here X, X, comma, 0, because X had the output 0. Finally, Z, we have a Y out here, so since Y has an output 1, so it's Y1 and Z2. So we basically fold in the output column into the input, but we do it by examining in terms of the next state. So this you will agree, I'm sure, that this is Mealy. So what is happening is, in case of more, in case of more, after the clock tick, like let's say I was currently in state Y, after the clock tick, depending upon the input, I would go either to state Z or state X. And when I go to state Z or X, then what would the output be? That's the output we are going to put next to it. And that is why Mealy reacts quicker, right? I'm not waiting for the actual transition to take place into the next state. We are kind of reacting to it immediately. So that's the Mealy machine. And then once you have this table, then going to the graph is obviously mechanistic. So one can easily do it. So hopefully.
A quick question.
Yeah, go ahead, please.
So why was Mealy Machine faster? Is it because you have like all the it's hard coded the outputs?
Yeah, can you say it again? Your voice kind of broke up.
Oh, so I was just wondering why the Mealy Machine was like faster than the Moore machine. Is it because like the outputs are like sort of hard coded into?
Yeah. So think about when we were sorry. So let's look at the state. Let me change color for a moment. Okay, let's say we were in state Y. So when we were in state Y, if input was 0, we would go into state Z, and then output would become 2. And if input was 1, then we would go into state X, and then output will become 0. Whereas in this corresponding Mealy machine, when I'm in state Y, if input is 0, output becomes 2 immediately. Then if input is 1, output becomes 0 immediately. And the transition to state Z and X will happen at the next clock tick. So the input is reacting before I'm actually making the next state transition. So so just key thing to point out is that these output values is what in the Moore machine would have been after the clock tick. Now it is happening before the clock tick. So the output changes are happening in the Mealy machine before the clock tick. Hopefully that makes sense. Right? So we are not copying, like when I was looking at Y, I'm not copying 1 into these 2 boxes. I'm actually copying what would it be in the next state in the Moore machine, right? I'm pulling that earlier. So that's why Mealy is reacting quicker. Okay, and you kind of see it also, right? I mean that the output values out here are a function of input, right? I mean, when I'm in state Y, output is 2 or 0, depending upon whether input is 0 or 1. So hopefully I kind of answered the question. So the important thing is that as I'm going from this table to this table, I'm not looking at the output in the current state. I'm now looking at output in the next state under different input scenarios. Okay, so that was Moore to Mealy, Mealy to Moore. But by the way, I mean, you could also argue that Moore, I mean, if I'm a Moore machine, then that's ipso facto also a Mealy machine, right? I don't have to do anything. It's just that one perspective you can take is Moore is a subset of Mealy, but that kind of would miss the point that there are benefits in terms of reaction time if I were to actually make the output immediately depend on the input. So that's the game that we did on the slide. So now let's look at Mealy to Moore. So let's say I have given this Mealy machine. It's clearly Mealy because like if I look at state Q0, then if the input is 0, output is, well, actually that one looks like a Moore. Yeah, let's look at Q2. So if I'm in Q2, if output is, if input is 1, then I self loop with an output of 0. And if input is 0, then I go to Q1 with an output of 1. So clearly, when I'm in state Q2, the output depends upon whether input is 1 or 0. So how do we convert this into Moore? Now here, I cannot even make the flippant argument that Mealy is a superset of Moore, right? I mean, so I have to do some creative thinking out here. So this is what we'll, so this is our original diagram, right? That when I'm in state Q0, if input is 0, then next state is Q1 and output is 0. If input is 1, next state is Q2, output is 0, and so on and so forth. So what I do is I create I look at these combinations of next state and output and think of them as a new state. So originally I had Q1 0, but now I have a state called Q10 and a state called Q11. Likewise, I had Q2, and so now I will have Q20 and Q21. So I invent these two new states. So essentially, I'm cloning Q1 into two copies, one which is for the case of input 0 and the other which is the case, one which is a case for output 0 and the other which is for the case of output 1. And likewise, I'm doing for Q2. For Q0, I don't have to do it in this particular example, just happenstance, because Q0, we enter and immediately leave. Okay, so it turns out I'm never jumping back into Q0. Okay. Then what I do is, so now Q0 remains Q0, but Q1 and Q2 get cloned into Q10, Q11, Q20, Q21. And then the output column basically follows from the name, right? Q10 output is 0, Q11 output is 1, Q20 output is 0, Q21 output is 1, and my state transitions follow from this time. Okay, so when I'm in Q0, when I'm in Q0, output is 0, and that follows. Like you can see, Q0 was like a more like machine state, right? Output was independent of the input. So when I'm in Q0, output is 0, and if input is 0, I go to Q10. If input is 1, I go to Q20, and so on and so forth, right? So essentially, I end up with a with a Moore machine, which has 2 more states, right? Instead of 3 states, I'll have 5 states. And that's what I have drawn on the bottom right out here. So, and that's why the original assertion, why does Mealy have fewer states than Moore in general? This is the reason why. That's the case out here. Okay, so this is how we convert Mealy to Moore. And what is changing between these two is there's a changing in output timing that is happening for sure. So you could say, look, they are not exactly the same. That is certainly true, but functionally they are doing the same thing. They're going to, if someone was sitting outside, right? I mean, kind of a God's eye view of the state machine, then they will, if I were to examine the input trace coming in and the output trace is going out, they will kind of look the same other than their timing behavior. Okay, so that's the main difference. Okay, so I can go Mealy to Moore to Mealy. And final issue I just want to touch is, and this has to do with kind of, so when we had discussed combinational logic way back, I had talked about the whole issue of hazards and glitches, right? That if I have a combinational logic, if the input changes, then if you are not careful, the output may see glitches in a temporary manner. We also saw it in ripple carry adder, right? If you add 2 numbers, as the carry ripples through, some of the bits at the output may flip back and forth multiple times before they settle, right? So we don't want that. We don't want, like, let's say I have the output and the output was supposed to remain stable. What we don't want is that the output goes back up and down like this. Or we also don't want like output goes back and forth before settle. Both of these are kind of bad outcomes. We don't want that. What we really want in this case is output should remain flat 0 or output should go clean 1 like that, right? That's ideally what we would prefer. So that's one kind of glitch. The other kind of glitch is that if I have a multi-bit output, right, then it could be that the 2 bits of the output may not change at the same time. So let's say I had 2 wires. And let's say the old value on these wires was 0, 0, and the new value is going to be 1, 1. But because of differences in speed, it may be possible that this remains 0, this becomes 1 first, and then 1, 1 come, right? So in that case, if an observer is looking at the system, it would see that the output did not just go from 0, 0 to 1, 1, it went from 0, 0 to 0, 1 to 1, 1. Again, we don't want that, okay? So these are all examples where output, if you're not careful, can exhibit glitches. And in general, our finite state machines are going to have that because, so let's imagine if I had a Moore machine, right? So in case of a Moore machine, the output combinational logic depends only on the state register. But this output combinational logic could be something really complicated, and the state may have multiple bits, and therefore the output may go, the effect of those different state bits may reach the output bits differently, and therefore the output may exhibit kind of the problems I talked about. So there may be glitches on the output. I don't want that. And worse, if I have a Mealy machine, then the input affects the outputs, right, through this. And in which case, glitches may be, excuse me for a moment. In which case, the output may see many glitches, and moreover, output may change middle of the clock. So if I'm observing the output, it may not be stable for a full clock cycle, whereas at least here the output would be kind of stable pretty much for the whole clock cycle, whereas here we may have, in the bottom one, we may have that problem that output may not even remain stable for long. So how can we fix this thing? How can we design sequential systems which don't suffer from glitches? In combinational system, if you recall, our trick to avoid glitches was to have redundant implicants into my design, so that kind of we avoided glitches. I sort of did work through a simple example in the lecture. How do we handle in case of sequential systems? So the trick is that combinational logic blocks are kind of bad in the sense that it's very hard to ensure their outputs don't glitch. We can do that prime implicant game, but then they come at significant cost. And then oftentimes you have modules like adder and stuff like that, and they have kind of this rippling of a signal, and therefore they give a lot of glitches. So instead, what we want to do is we want to make sure that my outputs come directly from a flip-flop with no intervening combinational logic. If we can arrange things to be like that, then flip-flops change on a clock tick, and so output would all change on a clock tick. And that is what we do. So kind of the idea is that what we want is the outputs to come from a register or a flip-flop, and not, so if I'm looking outside on the output pin, if I were to just trace back in, then the output pin, the wire from the output pin should be connected to the output of some flip-flop or register within my system. That's what we would like, because if we have that, then I'm assured of good behavior on the output. Flip-flops don't glitch because they happen instantaneously on a clock tick. So how can we achieve that? Well, let's imagine our original machine was a Mealy machine, right? So if the original machine was Mealy machine, it would kind of look like this part, right? That's the Mealy machine. And then what we can just do is we can just add an output register to it. So I'm kind of delaying the output of the Mealy machine by one clock tick. So therefore it's called as pipelined Mealy. No glitches on the output, but timing behavior has changed now, right? It's previously, this was the output and it was changing as soon as input was changing. But now I have a delay out here, right? I have added a D flip-flop or a clock register out here. So there's a clock tick delay. So it's referred to as pipelined Mealy. Moore machine, same issue. My original Moore machine was this. Here, even though the output only depended on the state, but there was this intervening combinational logic, which causes problems, can result in glitches. I can play the same game. I can put an output register. So Moore machine was already slower than Mealy, and now I am slowing it down by one more clock tick. I'm adding one more clock tick delay. This is called pipeline Moore. Okay, both of these are valid approaches. The problem though is that I'm delaying the output by a clock tick, and that's kind of ugly, right? I mean, you might think that, oh, a clock tick delay doesn't really matter, but this can add up in a complicated system. So you don't want to do it, and also we'll see 2 modules from now that adding pipeline delays like this willy-nilly can have consequences on a system where there is some sort of a feedback happening. So we don't want this. So pipelining, not really a good idea. We don't want to do that. So what do we do? So that leads to kind of a second approach, which is more clever, and which is that we store the outputs as part of the state. That's kind of the idea. So basically what we are going to do is we are going to encode our state such that some of the state bits directly correspond to our output bit. So let's say I had an output X, then what I'm going to make sure is that in my state register, there is a bit which corresponds to whatever the value of X is. So I'm kind of constraining my state assignment. And if that happens, then my output can just directly come from the state registers. Okay, so this is really playing with the state assignment, clever state assignment. Now, of course, it is constraining my state assignment, so it's possible that I may need more flip-flops than truly necessary. But the big advantage is output is coming straight from the state registers with no intervening combinational logic, and certainly no pipelining that is happening. Okay, so with a much lower cost, I can get the desired property, no glitches out there. So that's one way of thinking. This is often called as output coded Moore machine. Okay, that is, we are creating a Moore machine because output depends only on the state, so it's a Moore machine. But moreover, the state is being done such that if I have 10 bits of state, let's say, sorry, if I have 10 bits of output, then my state would have 10 bits at least, which will correspond directly to the output. And then I may have additional bits. We saw this actually in the example when we were doing one of the sequential design, where I had kind of covered a version of this where we kind of made output bits as part of the state. So we have kind of seen this earlier also. Another approach is what is often called as a forecasting approach. And kind of the idea is that instead of thinking of an output function, I think of the next output function. Okay, so I'll have my state register, but remember previously my we always had the next state function and the output function. But now let's imagine that instead of that, we are going to create a function called the next output function. And since it's a next output, I can then delay it by clocked it by a clock register. So these kind of machines look like this, that they have a next state function and a next output function. So I'm forecasting the output for the next clock tick as opposed to what is happening right now. A lot of people like this second approach. I find it confusing personally, but websites and textbooks say that this requires less thinking. So maybe I'm kind of more of a outlier on that regard. But this is another approach. I personally kind of like working with this kind of an approach. I think I find it more intuitive. But anyway, just wanted to mention, I guess a deeper issue out here is that you want the output of a sequential module to come directly from a register, not from the output should not come from a combinational logic, and certainly not from a combinational logic which directly has a path all the way back to the primary input out here. Okay, that would be even worse. So these are FSMs with outputs that are registered, as in they are coming, the outputs are coming from flip-flops. Okay, so that wraps up this module. So we saw concept of sequential logic, the notion of state registers, and kind of how we use next state and output combinational logics. We saw synchronous sequential logic in particular, where the state changes upon a clock tick. All bits of the state are updated at a particular point, typically the rising edge of the clock, for example. In essence, we saw that designing a sequential system this way really boils down to designing the next state function and the output function, two combinational problems. We saw that I can think about the state machine in multiple ways, as a state diagram, as a state table or state transition table, which has both next state and output in it. We kind of saw that. We saw that state assignment is a crucial part of the game, right? We have to think about what bits to assign states to states, and we kind of saw that most compact way of assigning bits is not necessarily the best one. And then one other thing we saw was state equivalence, right, which helps us identify states, pair or more sets of states which are equivalent, and then we can kind of collapse them. So we end up with a more compact state machine. It's kind of like we end up with a better algorithm, okay? And then finally, from an implementation perspective, once we have played all this game, it's basically a combinational design problem at that point. You're just creating implementations of two combinational functions. Okay, so with that, we end up with this module. And now we move to more complicated, or at least more interesting sequential systems. And so one of the key things behind the sequential systems we saw thus far was that all the inputs and outputs were like 1 bit, 2 bit. We were kind of looking, they were, or like we were not really doing any sort of complicated data processing on them. Excuse me. But there are many systems where we have memory, but the memory is actually values of data, right? Like, for example, if I were to tell you, tell me the median of the most recent 10 numbers that you see on the input, right? Let's say, so my system is always outputting the median of the previous 10 numbers. And those numbers are, let's say, 16-bit integers. Okay, so things like that. So a lot of signal processing, sensor processing, control, a lot of interesting systems fall into that category. So we need to think about sequential systems which are not only focused on controlling, jumping from state to state, but also processing data. And that leads to kind of this notion that finite state machines, which have two parts to it. They have a controller, which kind of is like the flow of logic in your programs that would be equivalent to your for loops and if then else and all, right? That's the controller part. And the data path are where I manipulate variables in the memory. So I do whatever variable A gets the sum of variable X and Y, right? So wherever we declare variables in the program, those are memory, and therefore they are part of the state too. And so the data path focuses on processing data, and controller focuses on orchestrating the flow of how we process the data. Okay, and we'll see this thing now. So, okay, so we are essentially now getting to kind of designing little computers. Okay, I mean, think of controller as kind of a program controlling the data path. Okay, so yeah, we've seen all of this. So, so the reason when you have sequential systems that are working with data, the problem is data have lots of bits, right? I can easily have a float 64. And so a single variable storing a number coming from a sensor, but it has 64 bits, right? Well, if it has 64 bits, that means I've suddenly added 2 to the power 64 states. That's load of states, right? I mean, so data, because it has data variables, because they have lots of bits, they kind of add to the state complexity a lot. So one way of thinking about it is, then how do we design systems where there are lots of states? Okay, but what makes these states different is that they represent data. They have some structure to them. They're not variables which are about the flow of logic, but they really are about variable. They're not representing state which is about the flow of my algorithm, but they're really representing state which is just capturing data memory. So let's see how to motivate this, and how do we think about designing these kind of sequential systems. And we kind of like to call them as, I think of my sequential system by factoring it into two parts: the control part and a data path part. So imagine you are making a 5-bit counter. Okay, so I'm trying to design a block which what it is going to do is I'm going to reset it. Count will become 0, and then every time I give a clock tick, it counts up. So upon reset, it goes to state 0, and then otherwise it comes to 1, 2, 3, all the way to 31, and then back to 0, right? And it repeatedly does that. So if I'm observing the output, those 5 bits would be kind of 0, 1, 2, 3, 4, 5, 31, back to 0, and they'll keep doing that ad infinitum. So if I were to do this, I can certainly draw this state diagram, no doubt. And I can certainly do my state chart and all. It will become clumsy. I mean, I'll have like lots of rows. What if it was a 32-bit counter? Now I'm in trouble, right? I mean, now instead of 32 states, I will have 2 to the power 32 states. Okay, so whatever, 4 billion states, right? Certainly I can't do it that way. So I need to find a different way of thinking about these kind of sequential systems than the way we have been doing thus far. Thus far, we had 2 tools at our disposal. We had the state diagram and the state chart, but we are seeing that they kind of explode. So, so we could attempt to do it this way, but it doesn't scale less. So, yeah, I've already made this point. So a better way to do these kind of problems is the way you write software. We think of processing the data. So if I were to ask you to describe this counter, you could more compactly describe it like this, think of like Python or C++ or something like that. I can say next state is equal to, anyone knows what this stands for? I'm sure you have seen it in your C++ or Java or Python kind of courses.
It's an inline if statement.
Yeah, it's an inline if statement. It's basically saying if reset is true, if reset is 1, then output 0, otherwise output state plus 1. Okay, that's what it is saying. And which is what we want, right? I mean, think about what's happening out here is basically saying if I'm in state, whatever, state 2, if reset is 0, I go, reset is 1, then I go back to state 0. Otherwise, I go to the next state, 2 plus 1, 3, right? That's what's going on. And then output is simply the next state in this case, right? I mean, the output is trivially simple. So counter is an example of what we call as a data path. It's a sequential circuit whose next state logic is described by a soft program-like expression. Okay, in some so that's right. It's very similar to programming. So we are writing a program where essentially you are writing an expression for next state, and you're going to write an expression for output also in a similar way. So now this whole next state thing, the table becomes much more compact. It's basically saying if the current state is A, I don't care what A is, then if reset is high, then next state is 0. And if reset is low, then it is A plus 1. This plus is now capturing a lot of detail, right? It's an arithmetic operator, which we have seen already before, right? We have seen how to do addition and all. So in this case, my next state logic is basically an adder plus, I guess there are many ways of doing it. You can basically say this looks like a little bit like a multiplexer, which is controlled by reset, and one input of the multiplexer is controlled to 0, and the other multiplexer is controlled to A plus 1. The student who just spoke, he said that this statement is like an inline if statement, and indeed a multiplexer is an if statement. So let's see how we can implement this. We can implement this counter like this, right? I can have a 2-to-1 mux. Next state has 2 choices, either 0 or current state plus 1. So kind of just an adder or a special case of an adder. And out here, reset controls the mux. The D flip-flop or the register is controlled by clock. And there I have my circuit, right? So now hopefully you kind of connecting it back to all those combinational modules that we have seen previously, right? They play the role of defining my next state logic. They are telling me how the memory in my system is being updated, okay? And big difference from what we saw in the previous module is that the next state logic kind of now looks like arithmetic expressions with some control thrown in. So that's a simple example. Let's look at more examples. Okay, so oh, by the way, the other thing I would like to say is that when you look at this thing, one thing which will strike to you is that there are 2 kinds of signals. Signals which are data signals, they are like n-bit, okay? And then there are signals like reset, which are affecting the flow of data, and they are like control. So reset is called as a control signal, and state in this case is like the data, right? So the control signals exercise control over how the data flows between register. Every clock tick, I take the data in the current registers and I process it through arithmetic circuits and all, and in this case, add incrementer and multiplexer and all, and then I update the state. Okay, so it's kind of like a program in which we update the variables which are there in my program, right? So this is where variables are getting, right? Data variables. So you see that there are n-bit stuff, that's data, and there is single bit or whatever few bit type stuff, which is control. I may have a counter which instead of like the same stuff will work, what 10-bit counter and 20-bit counter and 32-bit counter and whatever zillion-bit counter, right? I mean, so you can see that the data and the control will remain the same, just the data part will change. So a general view of data path type sequential systems looks like the following. There is a state register. Think of it like this is where all my variables are being stored. At every clock tick, I'm going to be updating some or all of those variables using a next state logic, right? And this next state logic may involve arithmetic and stuff like that. It will make use of the current state, current variables, as well as additional input which is coming from the outside. All of this feeds into next state logic. And then also we may have some output logic. We didn't have it in the counter, but we'll see it later. And that output logic will again have some arithmetic in it potentially. Okay, that kind of n-bit functions. Okay, and they will depend upon the current state, which is the current variables, as well as the input which is coming from the outside in case of a Mealy machine. So that's a general structure. It looks like any other, exactly like the sequential systems that we saw previously. The difference really is in the manner in which we are going to describe the next state in the output logic. We are going to be expressing it kind of like the way we express a program. Okay, so that's the huge difference of it. And since the number of bits is very large, we can't really conceivably draw state diagrams anymore or make state tables easily. Okay, so these are described by functions instead of tables through programming language expressions, if you may. So let's look at another example. Let's say now I want to make a fancier counter. This is a counter which has up, down, load capability. So it's a deluxe counter which can count up under control of a signal. So I have a signal called up. So if up is high, the counter will count up every clock tick. Count down, decrement, if down is high. And I guess there must be some priority between the two. So, and then load means that I can load a new value into the counter so that I'm not always just counting from zero. Okay. And then finally, there is a reset signal which forces the counter to be zero. Okay, so I can do up, down, load, and reset. Basically, just resets the whole counter. So if I were to think about how would I express this, the next state function of this counter, it will look like following. It's like a program, right? If reset, next state is zero. If not reset and up, next state is state plus one. If not reset and down, then next state is state minus one. If not reset and load, then next state is whatever is on the input signal. Otherwise, next state remains unchanged. Okay. Now here you might say, okay, but I mean, these seem to be all in parallel and all. So maybe you can think about like, I first, it's kind of like a else if, right? So you can say it's like this. So I can, and I guess the point I'm trying to make is it looks like you're writing a program really, and indeed you are, and this is why kind of hardware description languages like Verilog, but hopefully those of you get into computer systems will see in some future course, they look like they're just specialized programming languages. And what about the output? Output is trivial, count is state. Okay, output is count, and count is the same thing as our state variable. So that's what this counter is. Let's look at some more examples. By the way, if you were to do the table version, it will look something like this. It's like super messy. And if the number of bits were to go up, then the table will have even more rows. So I'm pretty sure kind of most people will agree that kind of writing things this way, thinking about it this way is a lot more elegant, a lot more compact. I can do tables in a compact manner also by resorting to symbols. So previously I had listed all the values of state, but what if I were to use symbols? If I'd say, if state is Q, then if reset is high, then next state is 0. If it is up, then Q plus 1. If it is down, Q minus 1, load, else Q, right? I could kind of write in a compact manner still, but still probably much better to do it this way. Okay, so yeah, so this is another way to express the state, saying state is Q. I don't care about the input. If reset is high, I don't care about up and down. And if load is 0, next state is 0. If Qx, if reset is 0, then we begin to examine up, down, and load. Okay, and begin to look at these signals. I don't know why I have put a 0 out here. Maybe it should be X. Yeah, that should be. Okay, and then correspondingly next state is 0 or plus 1 or minus 1, or we load the value of input, or we stay put. Okay, so a variety of ways of doing this thing. No one, honestly, I mean, other than in early stages of hardware, you probably won't be writing it in this way, and you're probably going to write it as a program. Excuse me. Okay. Sorry. And if you kind of think about it, what circuit element can we use to select these next states? Kind of reminds you of multiplexer. They're just different cases. So multiplexers play a very important role in this way of thinking about sequential systems, because I have like 5 cases out here being driven by different values for these signals. So you can think of that I have a multiplexer, which is a 5-to-1 multiplexer, or more likely 8-to-1, whose select signals is some sort of function of these things, right? Whose select bits are being driven by, not in, apologies. So whose is going to be driven by this. This feeds into select of mux. And this reminds us of mux. So that would be a way to kind of design it. So this is what it looks like. I can create a multiplexer. Now, the thing is, looking at that, we had 5 cases. 5 is a little bit ugly because I have to go to 8-to-1 mux. So what if I could do it in 4-to-1 mux? So that's what the slide does. So we think in terms of 4 cases. So how can I reduce 5 cases to 4 cases? Well, in the previous one, I had these 2 cases, +1 and -1. Maybe I have a combinational module which can do both +1 and -1. Then I can subsume it into a single case. So that's what we do. So we create a multiplexer. We take our reset, up, down, load signals. We feed it into some combinational logic which we design, and then the bits that come out of it, one hot coded, we use them to the multiplexer. Now I have 4 cases for the mux. One is count remains the same, another is load in, another is go 0, right? So if reset is high, then we load 0. We feed all of this into next. So this case is some module which is capable of doing +1 or -1, and that we are going to control with a down signal. We saw adder subtractor in a single unit way back when we were doing adder subtractor. So this is actually a pretty simple module to design. One way of thinking about it is that we do a 2 complement kind of a thing, and then we make it do plus and minus. We had seen that circuit actually with an adder and an XOR gate. So we have seen how to design these kind of things. So anyway, this is a structure. So as you can again see that the heart of a data path is registers which hold the variables, multiplexer which let you select between different cases, and then some logic which truly decides what is happening. And then also we will need some side logic which will control the multiplexers or provide extra inputs to the logic blocks out here. Okay, so there's a very typical way data path looks like. So this part is the data part. Here, data flows left to right, whatever n-bit data. This stuff is like now control. It's a very simple control, but it's simple. It's manipulating the control signals. On a chip, the data part will have wires running left to right. Let's say, for example, flowing the data, right? Input coming in bit, output going out bit, and then these control stuff is kind of sits on the side and then manipulates that flow of data. So that's an up-down counter. Still kind of more complicated than what we saw earlier, but still simple enough. So we are going to now look at some more examples. Yeah. Okay. So let's look at some more complicated examples on how we scale this thing up, okay, to more. So let's say now our ambitions have gone higher. Now we want to do a timer module. So timer is like a counter, except that counter just counts up and down, whereas a timer has this notion that I start the timer, and then when the timer reaches a certain destination, then it fires. Okay, so we use timer to time specific intervals of time, right? 1 second. So we kind of started like the timer app on your phone, for example. So we want to create this timer module. Typical use pattern is that we load a value to set the count to something, and then we start the timer and we tell the timer to start counting. And then when the timer reaches a destination value, typically counts down to 0, let's say, then there is a done signal, which will basically say, hey, I'm done, I've counted the time. So our timer, in this case, has following signals in. It has a reset signal, which resets the timer. A load signal, which loads a value into the timer, right? So I can set it to whatever, 45 seconds. Then I tell it to start counting, and then the timer counts down. When the count reaches 0, then it makes the done signal to be high. So that's kind of the idea, and the timer will, once it hits 0, it will stay there. Okay, so it fires. So that's kind of thing, a very generic timer, nothing specific about it. So let's think about how will we write this, right? So again, we'll have a state, right? And a next state for it. So now the logic will look like something like the following, if we kind of parse the thing. If reset is high, or I'm done and load is not high, then next state is 0, right? Because in one case I've reset, so I go to state 0, next state becomes 0. In the other case, I was done, I was at state 0, but since there is no load, I stay put at 0. Otherwise, if reset is not true and load is high, then next state becomes whatever is on the input to the timer, right? So this is entering a value into the timer. And otherwise, next state is state -1. So you're basically writing a little program, right? I mean, that's what we're doing. Now the output function here is a little bit more complicated. Remember here, unlike a counter, I'm not interested in the bits of the state. I'm not interested in the count. I'm interested in when the count has become 0. And that is what this guy does, right? Count, I want done to be 1 if state bits are all 0. So this is basically a NOR gate, right? Since I'm using a programming language syntax, that's why I'm using the exclamation point out here. In our logic expression terms would be the tilde sign, okay? But since we are in kind of trying to attempt to write it as a Java or C type code, so that's what we have. So that's a timer. Again, few lines of code, and then there are tools which can take descriptions like these and generate the logic for you, generate the finite state machine. Any questions before I move to more complex examples? So hopefully all of you have done some programming, okay, because this is where the world of software and hardware blend into one. Okay, so in terms of implementing, right? So we have to implement this. Again, we have multiple cases. That's our multiplexer. So I need a multiplexer which is 3 to 1, okay, or really in Logisim you will be using a 4 to 1 bus or something like this, okay. And we have 3 cases: load a 0, load the output, or take the current count and subtract 1 from it and load it. And then I will have some logic which is for the select. It will be driven by the reset signal and the load signal, and then also the done signal, right? All of them will feed into select logic. The reason it is that if you go out here, you would see done appears out here, right? So done is what we are outputting, but we're also using done in our logic. And then the final done part is really checking that all the bits is 0. So this is combinational logic also. So we see kind of this is combinational logic for output, right? This combinational logic is controlling the multiplexers. We didn't have to control anything out here. And then this is where flow of data is happening. Flow and processing of n-bit data. So the trick out here with these kind of problems is to kind of see what are my data variables, how are they flowing in every clock tick, and then everything else which controls how those data variables are flowing and how are they being processed, the n-bit variables, that kind of goes into your this logic which is sitting on the side. Let's look at another example. It's a shift register. This is something we have never seen before. So what is a shift register? So the idea is that it's a block, it's a sequential block. If reset, output is set to 0. Otherwise, on each clock tick, the output is like we have an n-bit number and we are kind of shifting it. So the output is one of the bits. The most we are going to keep shifting left, and output will be the most significant bit. So what do we mean by that? So let's imagine I have an n-bit state. So what this is saying is if reset, next state is 0, right? Next state is an n-bit variable. Otherwise, next state is, now what is this notation? This is concatenation. It is basically saying, think of an n-bit number whose lower bit is Sn. And so this is bit number 0. And these are bits n-1 to 1. And the remaining bits are coming from the lower n-1 bits of the current state. So we are discarding the most significant bit of the state and putting in a new least significant bit into the state and harnessing this. So we'll see shortly how it will look like circuit-wise, but we are I'm shifting the state left and taking my 1-bit input and shoving it into the least significant bit of the state register. And output is just whatever is in the state register. So this is how it looks like. It's really, the logic here is just a multiplexer, and like, so I have a clock driving the state, right? So this is where my state is being held. And then I have two choices. Either if reset is high, then I load a 0. Otherwise, now what you're seeing out here is really wiring. So what we are doing is we are taking bits 0 through n-1 of the state. We are ignoring the most significant bit. We are taking the lower n-1 bits, making them the upper n-1 bit of the new state, and we are taking the input coming from the outside world and putting it into the lowest bit. So all of this is just pure wiring. There is no cost associated with it other than cost of wire. There's no gates, I guess. I shouldn't say there's no cost. Wires have cost too, but there's no active logic out here. This you can use. You can easily implement something like this with the back to 2 splitters in Logisim. Okay, so if you were to do it in Logisim, then you can use Logisim splitter. Can help you implement that. Point is, there is no wiring, 0 cost. Sorry, there's no gates, 0 cost from a gate perspective. And by the way, I do want you to remember this notation because we will use it in upcoming PSETs, quizzes, finals. So I expect you to know it. Okay, so this is concatenation. This is from Verilog, so it's a notation from there. It's not something that I've invented. I know some of you have expressed concern to the department that I use unusual notations. Trust me, none of them are unusual. They are just coming from hardware-oriented languages, so you've not been exposed to them. This is one of those. This is just from Verilog. Okay. Let's move on. More sophisticated shift register, which is bidirectional. Okay, so another example. So now the previous one was always shifting left. What we want to do is now shift left or right, depending upon 2 signals, left or right. And then I have reset, and then I also want the ability to load a new value. The previous one didn't have a load. So let's see how will we do that. Again, problems like these, conceptually, they're actually not very hard. It's just the specification you have to parse carefully, right? You have to be very precise in reading things. That's the supremely important part, because that is where things go wrong. That when we don't read the specification with preciseness. So if I parse all of this thing, basically it's kind of saying, if reset, next state is 0. If not reset, other cases, if it's left, then this is like the case of the previous one. Next state is the lower n-1 bits of current state. And then this is from outside. So I'm shifting left and putting the bit coming from outside at the LSB part. If not reset and not left, but rather right, then next state is, so I put shift in SN on the upper, and now this time around, I'm looking at the upper n-1 bits. And again, this curly braces is the concatenation operation. And finally, well, not penultimate, if not reset and not left and not right, but load, then next state gets the new in. Okay, so there are 2 inputs out here. There is an n-bit input, and then there is this SN. And finally, if everything else fails, then next state stays put. And output is simply out equal to state. So super simple. The schematic looks like this. I have now 5 cases going back out here. there are 5 cases, right? 1, 2, 3, 4, 5. So multiplexer, which is a 5 to 1 mux. Again, in real life, multiplexers are powers of 2 to 1. So you probably need to use an 8-bit, 8 to 1 multiplexer. 5 cases. So 0, load in, maintain the state, shift right, shift left. These are again just wires. And then the select signal to the mux is going to come from the signals we have: reset, left, right, and load. So this combinational logic you will have to design. This part again follows from your program. Okay, so any questions on what's going on out here? So so faced with a problem, you kind of write the pseudocode, if you may, for 2 things, right? Next state and output logic. But now instead of state diagrams and all, we are kind of thinking of it as almost like a software program. I'm writing 2 functions in a programming language. Again, remember, these are just wires. So to summarize the example, these examples, all of these are sequential systems, but we are kind of designing them in this manner where there is a part which is what we are calling as data path. It processes data, processes n-bit things. And then there is kind of this glue logic, which is sitting next to it, which kind of controls how the data are being processed, which case gets done. And then all my variables, they're memorized in the state register. So the purpose of the state register in this case is to store the data variables. There are, you can think of it like a divide and conquer approach. I am dividing the problem into kind of this 2 halves, data and control. There are variety of ways we can partition sequential systems into simpler things. There is another approach which is often used, kind of analogy with software, master slave or client server, right? I mean, so what we do is we kind of factor out part of our functionality into one sequential system, and the other sequential system hands jobs to it, or control it as a superior to the one finite state machine is acting as some sort of a superior to the other one. Controller data path partitioning. In this case, the next states are being computed using the data path, but data paths are being controlled by some sort of a control logic, which in itself could be a traditional finite state machine with state graph and all. So I'm going to talk about how to do this kind of a design with a more complicated example. Okay, you can think of it as if I'm designing a dedicated application-specific computer of sorts. Okay, a general purpose computer like your microcontrollers and microprocessors are basically also controller and data path. They're just more general purpose. Their task is the input to them is a program, whereas in our case, we'll shortly see, we'll see a vending machine, the program is fixed. So the difference is what the input is versus kind of anything more fundamental. So we are going to look at a vending machine example. I'll probably not do the combinational log, just focus on the vending machine. It's from the textbook. So if you have the textbook, you can look at the machine there. Okay. So what happens is that oftentimes now we are given very complicated specifications, okay? Not simple like timer and stuff like that, but really kind of more sophisticated things. Controlling a radio, controlling a vending machine, a car or vacuum cleaner or stuff like that. So one way of thinking about these systems is like the following, that there is a data path where we process the data. And then there is a controller which orchestrates the data path. And in general, this controller may itself have states in it. Okay. Our example thus far, the controller was just some little combination logic, but it could be more complicated. And then the way things happen is there are signals coming from the outside world, which are like control signals, and outputs going to the out, which are control outputs. These tend to be few bits. They're like handshake signals, 1-bit sensor signals, those sort of things. And then there is n-bit data. I'm using n as in just to indicate that these are really data to be processed. They are not telling, generally they are not encoding directly, at least some sort of a control flow. And so like control input may be the user pressed a button. N-bit data may be the microphone sound sample. Okay. At a deeper level, they're all the same, but kind of for practical purposes, we handle n-bit stuff with arithmetic, and we handle these buttons and all to control the flow of arithmetic. The two halves talk with signals with each other. This control FSM sends commands to the data path. This is kind of like the instructions in a computer. I know probably many of you are doing CS33 and you have seen the structure of a computer. So these are like the opcodes in a program. Those who haven't done CS33 or don't intend to, just think of them as these are instructions coming from the controller, which has following some instructions and sending it out here. So these are instructions. And the return is status. This is basically the data path telling the controller something of interest. Like, for example, the data path may say there is overflow. Or divide by 0, or such thing, exceptional conditions which need attention, right? Which will affect the flow of within the controller. So like controller will examine the status, and then based upon that will decide what command to send next, right? So in a program, these are like the condition part of if or multiplexers and all, right? So faced with a complex problem, we kind of divide. This is a way to think about it, right? There are two parts to it. There is stuff which is controlling the flow of information, and the stuff which is the actual flow and processing of information. So data path computes as next state. They are the state in the data path out here is like program variables. And there are going to be multiplexers and modules like adder, subtractor, stuff like that, arithmetic stuff and all. And the controller internally also is a state machine in general, and it computes its next state via state table, state diagram. So this is the stuff. This is from the previous lecture. Sorry. Oh, God. Messing things up. Okay. My apologies. Okay, so the control FSM is how we do the traditional design, and data path FSM, right? Both are FSM, is done using what we learned earlier in today's lecture. So control FSM sends commands to data path sends back status. Input and output to the system are, so from the outside world, we are getting these two inputs, but you can think of them, some of them go to data path, they are like the n-bit stuff, and some of them go to the controller, they are like single type signals. And likewise, on the output side, we have the same story. Main thing really is that the separation of control and data is not always clean, and there is no one right answer. Many problems can be solved entirely as data paths, and many problems, simple ones, where you don't have data or the data are very few bits, like 2 or 3 bits maybe, then they could be done entirely using control FSM. More generally though, you will see that data tends to have lots of bits, like stuff coming from sensors and all, maybe 32-bit floats and all. The moment you see arithmetic, you should probably think data path. The moment you see complicated, whatever, a neural network or these kind of things, that's like data path. And the moment you see if then else and those kind of things, you should think of control FSM. But the boundary is not that thin always. So I can think of it as, if I look at this control FSM, it really has 2 types of inputs. It has inputs coming from outside, and it has inputs coming from the data path. And it has 2 types of outputs. It has output going to the outside and outputs going to the data path. So control FSM, if I were to think of like what is its, how am I designing it? I'm really designing it to consider all these inputs and outputs. And likewise for the data path. Data path is getting 2 types of inputs, that from the outside world and the inputs coming from the control FSM, and it is producing 2 types of outputs, those going to the outside world and those it is sending to the control FSM. So I'm designing 2 FSMs, one using the previous lectures methods and one using the current lectures methods. So, and that's how kind of we end up dividing things. So now let's jump to an example, complicate, far more, probably the most complicated example we have had in lectures thus far. So it's a vending machine controller. Okay, kind of vending machines that sort of we all see. So this is, but simplified one. So this is a vending machine which can receive coins, nickel, dime, and quarter. So 3 kind of coins. And as you put the coins in, it will accumulate the sum. So some sort of a display will tell you how much money you have deposited. Then at some point, you are going to dispense. But this machine has only 1 item to serve. So it's nothing like what I've drawn out here. So imagine it has a drink. And when you press the dispense button, it will dispense that item, provided there were enough coins which were deposited. And it will also return the change 1 nickel at a time. So, and of course, there has to be a price for that item. Okay, so essentially we have to make sure that you have enough items. So we'll need, already you can see that there is probably some sort of a comparison we need, right? Compare money deposited with the price. And then whatever is the difference, I have to return nickel at a time. Moreover, there has to be some mechanism to actually dispense the drink. So imagine there is some sort of a mechanical gizmo where I can tell it, go ahead, dispense the drink now, right? So when the dispense button is pressed, our finite state machine will have to then, our sequential system will then have to tell that motor mechanism dispense. Now the motor operates on a mechanical time scale. So it will take presumably many seconds. And so meanwhile, we'll have to spin in a state. And then when the motor sends a done signal, that the action is done, complete, the item has been dispensed, then we are going to get that done signal back. So if you kind of ponder over this, clearly I need a data path because I need to do all this coin arithmetic, right? How many coins have been deposited? What's the price of the object? How much money do I have to dispense and all? And then I will need some sort of a control machine, control FSM, which will orchestrate all this stuff, right? When to tell the motor mechanism, when to tell the coin disposal mechanism, and so on and so forth. So, so it's the part which interacts with the physical world signals that this machine is seeing. So yeah, so no, there's a single ring. User has to press a button, coin-based, nickel at a time. So let's try to design this. So I'm receiving coins. So you can think of the act of receiving coin is like a event of some form, right? We have to track it. Okay. If you noticed, nickel, dime, and quarter, they're all multiples of 5. So maybe I can just get away with things in terms of nickels, right? That dime is 2 nickel and quarter is 3 nickel. So my arithmetic could be simpler. Nickel means add 1, dime means add 2, quarter means add 5. When dispense button is pressed, the drink is served, provided enough coin has to be deposited. So clearly we need to know the price of the drink, but hopefully it can be hardwired in, it's fixed. And then we return the change 1 nickel at a time. So in this state diagram, for sake of simplicity, self loops have been eliminated. Okay, so basically the idea is so the idea is that if the condition is not met, like let's say I'm in change 1, if done is not high, then I remain at done, at change 1. Likewise, at every state. So if by default we stay put in that state, that's kind of the idea. So what is happening out here is that I'm going to start out in a deposit state after reset, right? So this is the reset signal, takes us to deposit state. And we are going to stay there, and the user can keep depositing coins, but I keep track of, has the user deposited enough coins? And the moment user has deposited enough coins, and has the user pressed the dispense button, right? So both these conditions have to be met. So I have to keep track, right? Did the user press the dispense button, and has the user deposited enough coins to exceed the price of the drink? If so, we move to the serve 1 state. In the serve 1 state, what we do is we tell the motor, serve the drink. Then the motor will come back with a done signal. So we stay in serve 1 as long as the motor does not send the done signal. Once the done signal comes, I get to serve 2. Now here, there are 2 possibilities. So when the done signal comes, we move out here. Now what the motor will do is it will give us a done signal, and then it sort of pull it down also. So done signal is some sort of if I look at the done signal, it's perhaps something like this. Okay. So what I do is I stay in serve 2. Now there are 2 possibilities. User had deposited exactly the change, or the user had deposited excess change, right? So excess case versus exact case. If it is exact, so once the motor pulls the signal down, and 0 means I don't owe anything, right? 0 means nothing owed, then I return back to deposit. If on the other hand, it was not 0, then I have to return the change. So again, I go to the dispense mechanism and I ask it to dispense, but this time around, I stay there until I actually get to 0. So I go back and forth, more and more nickels, right, dispensed until 0 is hit, and then we kind of come back to deposit. So it's a very abstracted state machine. Obviously, a real machine would have, even a real machine of this, real implementation of the simplified machine will need a lot of details to be worked out, but that's basically happening. So let's walk through the states. In deposit, we are continuously sitting there waiting for coins. In serve 1, we are waiting for dispense. In this case, in serve 2, we are kind of checking. We wait for a nickel to be dispensed and checks again that, and then we go back. So if I kind of pull together, sorry. Yeah, so if I pull together all of this, then a machine looks like the following. I have a price. This is hard coded into the system. Okay, let's say 20 cents, something like that. This is the state where I'm tracking how much money I owe, the machine owes to the user, right? So you can say money owed to the user. Now, we have broadly three things happening. One is upon reset, we have to set it to 0. So that's this case. Second is if nothing is happening, we stay put. So this is stationary. And otherwise, we have to do some arithmetic. And the arithmetic part is two things going on, right? One is I'm depositing my coins, and the other is I am consuming, dispensing drinks and dispensing coins. So I need to do plus or minus both, right? So by analyzing this, you can begin to see that, in this problem, I have to subtract and I have to add. And what do I need to add and subtract? I have to add and subtract a nickel or a dime or a quarter. So I need these constants, 1, 2, and 5. Moreover, I need to subtract the price. So I need the price also. So I can have this multiplexer, which basically helps me select what the right constant is. So this multiplexer selects the value. So some sort of a signal which comes from my control tells me the value, and then I am going to add or subtract that value to the current money owed. So this structure, right now we are just going in faith. We are saying that, look, this problem requires us to do these things, right? So I'm kind of just building up the hardware necessary for it. I will need to add when the user deposits a coin. So I need to be able to add 1, 2, and 5. I need to subtract. I need to compare, right? So I'm going to build up those functions. So that's the manipulation of the money owed. I need to do the comparison for enough. So I need a comparator also out here. So I put down a comparator, which compares the current money I have in the machine and compares it with the price, and that gets at the enough part. And I also need to compare when I am down to 0, right? That I don't own any more money. It was exact. That's the 0 part. And I need to send money to, I need to send a signal to the drink dispenser and to the nickel dispenser. So those would be output, some mechanism. So this goes to mechanical. And then finally, I must be getting these kind of signals, right? Reset, nickel, dime, quarter, dispense, done. So at this point, when you're designing something like this, you're kind of going back and forth with your customer in a way, right? I mean, because your signals partly come from the mechanics of the machine, buttons and all, and they go to the mechanics of the machine. So you'll have to kind of think about, like, what is the best way of doing it? If it was a car or a drone or whatnot, these are going to be coming from the sensors and the motors and all the things. So this is where either you are given these signals and then you just design for it, or more typically you are kind of designing what the signals should be and what my finite sequential system should do, all of them together. So once we have all of this, then our task really boils down to writing a program on this control FSM. This is a little program, which is often referred to as microcode or firmware, all sort of names given, okay, or just hardwired logic, right? So this is there are two parts of this design now. One was kind of architecting the data path, making sure that my data path has all the abilities that we need to be able to pull off this task, right? All the functions that we want. And then the actual orchestration of those functions, we put it into the control FSM. So this is code, and this is kind of like getting the right computer, right? Getting the right operations that I need to do. And so that's the control logic. Yeah, I think select add. So when depositing, we add an incoming coins amount to the deposited amount. So that's what we do. When returning, we are going to subtract the price, and we are going to subtract the nickels. Okay, so that's how we are going to control that. Which do we add? Like, how should we? This is like, how should we update, right? So this is the multiplexer doing that. Yeah. So depending upon the various options, I may select the sum, I may select an amount of 0, or I may just retain the value. So at this point, like looking at this, if when the user is depositing the coin, let's say the user deposited a nickel. So you are going to select one, you are going to select add, you are therefore you are going to select this sum, and then go out here. If the user were to dispense, then I'm going to select the price, I'm going to select subtract, and then do this. So for every operation that we need to do, there will be some combination of these three signals which will let us do the task, and you have it's your job to make sure that that's happening. Enough and 0 are always available. There's nothing, we don't need to control anything out there. Once you do all of this, so now you have built a computer and you have written a program for it. Yeah, that we have already seen. We store the value out there. We've already seen that. Once you have done that, then
Sorry,
yeah, go ahead, please.
can I ask a quick question?
Yeah.
So just to clarify, does the FSM diagram or like state diagram from a couple slides ago, is that referring to the entire
No, it's referring
like
to
system or just that part? Okay.
just that part. Just that part. Yeah.
And
So-
everything
so
else
that-
is like the data
Yeah,
path.
although
part of it.
right. So everything other data
Okay.
path. So you're really designing two different finite state machines, right? This is also a finite state machine. It's just the data path part of it, and so you call it. This is a data path FSM, or simply data path, and there's a control FSM. And just for everyone's benefit, what you are referring to is this guy here. This is for the control FSM part. Okay, it's abstracted away in this example just because there are a lot of details, but they basically are that. Okay.
Awesome, thank you.
Sure. Okay, so now let's go to this diagram out here. So this is just a machine in operation with a little timing diagram out here. Just to see what happens. So you see at the start, it is doing a reset. So I'm going to walk through the animation. Okay, my animation. So at the beginning, there's a little reset. And that reset, as you see, reset the amount to 0. So at the clock tick, it sets the amount to 0. Okay, that's all we care about. Everything else is secondary at that point. Then what happens is the user deposits a nickel. So when the user deposits a nickel, we expect some amount to increment. So the user deposits a nickel here, and so then you see the amount goes to 1. User deposits a dime. So now there are 2 more things, so the amount goes to 3. Then the user attempts to dispense. So presses the button, so we get that signal. Unfortunately, 15 cents is not enough. So the user deposits 2 quarters. So we get an 8 and a 13. Then the user presses a dispense. And at that point, it seems like 13 was enough. And so when the user presses a dispense, the amount of the price is deducted. In this particular case, sounds like the price was 55 cents. So we are left with 2 nickels worth of, or whatever, 10 cents worth of money in the machine. And meanwhile, if you look at the dispense, somewhere should be, yeah. So serve, yeah. So this is where the serve signal And then once a serving is done, then there is a done signal which comes up, right? So that's kind of like a handshake with the machine that is happening. Meanwhile, you can also see whether there is enough and zero. So this is where enough had gone up because there was enough money in the machine. So that's what's happening. And then at this point, since we had leftover change, so the zero is low. So we are going to start dispensing change. So we have to dispense twice. So that's going from us to the mechanics, the mechanical part of the machine. And then after dispensing 2 nickels, the amount goes to 0 and 0 goes high. And we are back to square one. Okay. So served ring, return the first nickel, return the second nickel. That's the sequence that's happening. Okay. So this is a simple run through kind of what may happen. There are a lot of other things you can look at, kind of what the state looks like and all, but those are kind of the high level things that's happening. So how to, like, I mean, this, there is no like fixed guidance for this because this is very problem specific kind of a thing. So the main thing is really given that plain English description of the machine, kind of your human like architecting has to come in, right? From that specification, what should be the data path, what should be the state machine, and then kind of building those things. Fortunately, though, nowadays there are tools which can even go from that kind of a high level description, even plain natural language description. And in fact, you can attempt to try some of these things out with ChatGPT and all, and you'll see that oftentimes they give reasonable guidance on how to go around building these things. So while I keep saying it's a human creativity, but actually there's a underlying pattern that flexible software. So while we cannot describe an algorithm to do it, but these modern AI tools and all are able to do a reasonable, at least a reasonable first cut job at these things. Combinational log example. Do I have time? Yeah, I have time. Okay, so here's another one. So in this case, I'll probably just leave it for you to do it, but I'll describe the system. So accepts input from a decimal keypad. Since there are 12 keys, so each key is represented using a 4-bit code, and then another bit to tell whether the key was actually pressed or not. The user presses a sequence of digits and then presses enter. So there must be some enter button, probably maybe either this or this, I don't know, something like that. If the sequence was correct, then if the sequence was correct, then the finite state machine is going to send an unlock signal to the actual lock mechanics, and then to lock the lock again, to relock, the user has to press the enter signal again. Okay. If the signal was incorrect, then a busy output is asserted. So presumably some sort of LED goes on, and a timer is activated to lock out the user for a certain predefined thing, right? Typically these locks, when you present an incorrect key, then they lock you out for a while so that you can't repeatedly try the key again. These signals need to be pre-processed so as to make sure, like when we say valid, so a problem that you face in these kind of systems is that our electronics or the underlying computing operates with high clock rate. Whereas when we humans press a button, let's say we press a button 4, then we are pressing it for milliseconds, tens of milliseconds. And so 4, when we press, then it's being pressed for many thousands of clock cycles. So one of the first things that one will have to do is to kind of arrange so that a single press of 4 is treated as a single press of 4, not multiple presses of 4. So there has to be some pre-processing so that the signals, and it is seen by a state machine, is only for one clock tick. So usually what we do is, instead of letting our main finite state machine worry about this part, we kind of create simple finite state machines which clean up the signal. So they will take a long lasting signal and they will convert it into a single clock cycle signal. That way, our main finite state machine will only see one clock tick signal for each button press. And then now you can go ahead and one can go ahead and begin to design these things. So like I can design how do we once we have cleaned up those signals, then at that point we can think in terms of the broad levels of my locking state. So I'm enter, we wait for the key to be pressed, the right key to press. When there is a match, we go to open and go back. Otherwise, we lock the user out. So if there was a failure to match, then we want the user to be locked out, stay busy for a while, and then kind of head back. Okay, so the lower part of this finite state machine is kind of handling the case of incorrect entry, and the correct entry is there was a key match and enter, and then we go back. So there's a lot going on inside this lock in terms of matching the keys, and one has to be super careful not to design it in a way that the user can easily fool it. So we start in an enter state. We get K match and L match from the data path. So K match and L match are signals coming from the data path. Their meaning is as shown below. So imagine so via this, I'm kind of still imagining something about my data path. We have not actually implemented the data path. So we are basically saying, let's imagine K match is a signal that the data path computes, and it tells me whether the entered keys match a subsequence of the code. So let's say my code was, I don't know, 4, 5, 6, 7. So if the user presses 4, it's a subsequent. User presses 4, 5, another subsequent. User presses 4, 5, 6, also subsequence. If the user presses 4, 5, 7, it's not a subsequence. So K match is telling me that whether there is a potential match of the key between what the user has pressed, entered thus far, and the thing. L match tells whether the length of the entered keys matches that of the code. So we are keeping track of how many keys have the user pressed this way. So kind of the idea is if the user presses more keys, then we want to reject. We don't want the user to just randomly press keys and we are tracking it and we unlock, right? So if the user presses lots of keys, like my code was 4, 5, 6, 7, if the user presses, let's say 3, 4, 5, 6, 7, I don't want it to unlock. So what we are doing is we are kind of doing a match on the recent 4 keys, but we also want to make sure that the user doesn't present more keys. So that is L match. L match is whether we have matched it properly or not. So the length of the entered key matches that of the codes. So we stay in the state as long as the correct digits are pressed. So kind of the idea is that as long as the user is pressing 4 or 4, 5 or 4, 5, 6 or 4, 5, 6, 7, we stay in the enter thing. If the user violates, either presses an enter and there was a length mismatch, or if there was ever a key mismatch, I go to these delaying states. So unlocks if in the enter state and enter is pressed and the length matches. So all those conditions have to be met. Then so my data path conceptually at this point, we are tasking it to create L match and K match. So I think we have already described this. If we stay there, move on. So 2 error conditions, enter and failure to match length or failure to match key, and then we go to wait 1 and wait 2. So that's our lock. And now we need we need to make sure, we need to validate that there will never be a case that the user can sort of fool the clock. So we don't, what we So the point out here is you have to think very carefully that if the user presses an enter at certain point in time, I'm going to skip this slide, but you have to just make sure that there is no loophole in your logic also out here. Okay, otherwise your lock will be insecure. And then finally, what is happening is that now we have defined the controller state machine. Now we know what my data path has to do. My data path has to provide me with K-match and L-match. And by the way, I have to send commands to it to sort of control things a little bit. So the data path will need to have some sort of a counter to match against the key. I have to have some sort of a ROM in which I have to store the correct code, right? I have to check whether my code and the key match, okay? And there may be multiple, the digits of the code are going to be stored in the ROM, so I have to kind of scan through it. So this counter provides me index into the ROM to kind of look at the right digit. I need a timer so that I can wait. So that's the done part. Timer we have already seen. And then I need to have a match for the length, right? So the length match and the actual key match. So the way we kind of went around doing this thing is we are kind of looking at in the vending machine example, we started with the controller FSM, and then we designed the data path. Here also we did the same thing. We started with the controller FSM, and then we designed the data path. Typically, that's the pattern you would see, that you first think about the high-level flow of your strategy, and as you go along, you are also sort of dictating or defining what your data path needs to do, and then you dive into the details of the data path. So that's kind of what is going on out here. Compares length and value of code, and the code is stored in the ROM, and the number of keys pressed, I think, and there is a timer logic. So again, no one recipe for this. The TAs are going to cover some more examples on how to do these kind of problems. Like anytime you have an iterative program, so I think one of the things we tend to cover is things like computing GCD of two numbers, those kind of things, so little programs, the kind of stuff you might do in a software course. Essentially, we are trying to do it with data path and finite state machine. So I'm at the end out here. So in summary, data path are also state machines. It's just that they are specified by an expression with arithmetic and multiplexers and stuff like that. So you are going to see those kind of entities, building blocks out here. And then given faced with a problem, we kind of divide it into a control FSM and a data path FSM. You have state in both. It's just that the state in data path tends to be huge because we are dealing with n-bit entities, right? I mean, if I'm doing arithmetic on 32-bit variables, then my state registers are huge. Whereas control FSM tend to have very few states, relatively speaking, for sure. So advice regarding this kind of stuff. So the thing I would basically say is, in some senses, good design cannot be taught in the sense of I cannot give you a recipe for it. No more that I can give you a recipe for how to go around writing software programs. It just comes from thinking, solving lots of different things. What I can suggest is that what are the signs of good design versus bad design. So if your control FSM is getting very complicated, that's usually a sign that you did not partition think correctly, or at least you are not thinking about the problem cleanly. What helps is that as you see these different examples, kind of try to distill them into patterns that work, much like in software, right? I mean, we learn about like different idioms of programming. It's the same thing with hardware. There are idioms of hardware design, and you, as you get more experience, you kind of, next time you face a problem, you would basically say, aha, this corresponds to something that I have seen previously. Okay, and kind of you don't start from scratch. Okay, so with that, I'm going to stop out here. Any questions before I hang up? I can do a little bit of an office hour if any one of you have questions on the design assignment or the PSET. Okay, if not, then I'm going to hang up at this point.